Analyze and sketch a graph of the following function. Label any intercepts, relative extrema, points of inflection, and asymptotes. All of this information that is highlighted here, the intercepts, relative extrema, points of inflection, and asymptotes, tells us everything we need to do for this function to sketch a graph of what f of x looks like successfully. The first thing I want to do is find the intercepts, and even better, I want to find the x-intercepts. So what I'm going to do in order to find the x-intercepts is to make sure that the y variable is set equal to 0, and then you just take whatever's left and solve for x. At this point, it is exactly the same idea as if we take this factor and set it equal to 0 and solve for x, and this factor and set it equal to 0 and solve for x. Now that first factor, you just get x equals 0. That's easy enough. And with the second factor, you get the square root of 9 minus x equals 0. And if you square both sides, you get 9 minus x equals 0. And if you add x to both sides, you get x equals 9. And one other thing I want to mention here is the domain of f of x. The domain of f of x is negative infinity to positive 9. And we can include that 9 because substituting the 9 into the original function here does not give us any undefined value. However, if you try to substitute anything bigger than 9 in here, inside the square root, that will give you something imaginary, and there's no room to graph anything imaginary on our coordinate plane. So we have an x-intercept of x equals 0, and another x-intercept of x equals 9. That checks out. So these are the x-intercepts. The next intercept I would like to find is the y-intercept, and I'm going to do that in blue. And the y-intercept is when you substitute 0 in for x and simplify. So that's 0 times the square root of 9 minus 0. Well, 0 times anything will just give you 0, so we have a y-intercept at y equals 0, or more specifically 0, 0. And more specifically up here with the x-intercepts, we could write these as 0, 0 and 9, 0. So we have some actual ordered pairs to put on a coordinate plane. And lastly on this page, I want to take care of the asymptotes. There are no asymptotes for this graph. If you'll remember, one of the ways we could have vertical or horizontal asymptotes is if there is a denominator in the original function, and there is no denominator in the original function. So we will have no asymptotes. On this page, I will be finding the critical values and thereby finding the relative extrema, and then finding the points of inflection. So here's the original function. I'm going to rewrite this as x times 9 minus x to the 1/2 power. And once you rewrite it like this, it is much clearer to see that there will be a chain rule going on here if you take the derivative of this part. What else is rather clear to see is that there is a product of two algebraic expressions, x and 9 minus x to the 1/2 power. So we'll have to use the product rule to find the derivative. F prime of x will equal the first times the derivative of the second using the chain rule. We will bring down the power, leave the insides alone, and subtract 1 from the power. Then to that we have to multiply the derivative of what's on the inside. So we multiply all of this by -1. To that we will add the second, that's 9 minus x to the 1/2 power, times the derivative of the first, which remember is up here, is just x, that is 1. From here, to get something nicer to work with, I'm going to simplify this derivative a little bit. This will be -x in the numerator of this first term because of this x and this -1. And that will all be over 2 times 9 minus x to the 1/2 power. That -1/2 power up here tells us to flip it to the other side of the fraction, change the exponent to a positive number. And then over here on the left, or on the right side, there's a 9 minus x to the 1/2 power. And so this is the derivative for our function. And in order to find critical values, you have to remember that critical values are where the first derivative is undefined and where the first derivative equals 0. It's always best to check for the undefined values first. You can see that there's an x in the denominator, and if you set that entire denominator equal to 0 and solve for x, you'll get that x equals 9. And this is where f prime of x is undefined. The other way to find critical values is to set this entire expression equal to 0 and solve for x. So over here, we will do that. 9 minus x to the 1/2 power plus 9 minus x to the 1/2 power. And my first go-to step is to always get rid of a denominator. And since there's a denominator here, I want to multiply all three terms by that denominator. 2 times 9 minus x to the 1/2 times 9 minus x to the 1/2. All right, what that does is when you do that, this entire expression will reduce with that entire expression, leaving you with a -x. And over here, in this second term, when you multiply something by itself, you can add the exponents together. 1/2 plus 1/2 is 1. So that is a 9 minus x to the first power. So that takes care of this term, and there's still this 2 that we need to multiply there. And on the left side, I didn't even write it in because 0 times anything is still 0. And when you solve this for x, distributing the 2, -x plus 18 minus 2x equals 0. You can combine the x's to -3x plus 18 equals 0. And when you finally go through and solve for x, you'll get x equals 6. And this is where f prime of x equals 0. So we have two critical values, x equals 6 and x equals 9, to consider for relative extrema. On this page, I have done some simplification to the first derivative, mostly making sure that this fraction in this term and this term can be combined together. And the only way you can combine something that is a fraction with something that is not a fraction is to give it a common denominator. Over here in blue, I am multiplying the top and bottom of this fraction times 2 times the quantity 9 minus x to the 1/2 power, so that I get a similar denominator in this term. And once you do that, you'll end up with something like this, and this is going to look similar to what we were doing when we were solving for x in the first derivative. So this here is a simplified version of the first derivative, and the whole point in doing that is to make finding the second derivative easier. So in order to find the second derivative, we will need to be using the quotient rule. So the second derivative is the denominator, 2 times 9 minus x to the 1/2 power, times the derivative of the numerator, which will just be -3, minus the numerator, -3x plus 18, times the derivative of the denominator, which will include a chain rule, which ends up being -1 over 9 minus x to the 1/2 power. And all of that will be divided by the denominator, 2 times the quantity 9 minus x to the 1/2 power squared. And in order to find x values for possible points of inflection, we need to find where the second derivative is undefined. And it looks like that the second derivative is undefined at x equals 9. And the other way to find x values for the possible points of inflection is to set the second derivative equal to 0. And the second derivative equals 0 when the numerator is equal to 0. Minus x to the 1/2. Because the only way a fraction can be equal to 0 is if the top number is equal to 0. So when you use a similar solving technique to get rid of this denominator, like what I used in the first derivative, you'll see that the x value is 8. So this is where a possible point of inflection can happen. And we need to check the concavity on each side of 8. But when you do this, keep in mind that you have to pick a number between 8 and 9, because the second derivative is undefined at 9, but also is undefined for any number bigger than 9. If you look back up here in the second derivative, if you try to substitute a 10 in for x in the denominator or in the numerator, or anywhere, you will see that you'll get something that is imaginary, and that cannot happen. So we cannot pick any values bigger than 9. It occurs to me that when I say this, I look over here, and this 1/2 should be on the outside of that set of parentheses. So, coming back to the sign chart, we can pick a number to the left of 8, say 7, and evaluate the second derivative at 7. And then we can pick another number here like 8.5 and evaluate the second derivative at 8.5. And when you do this, you'll see that f double prime of 7 gives you a negative value, and f double prime of 8.5 also gives you a negative value. So in between 8 and 9, this graph is concave down. And also in between negative infinity and 8, that this graph is also concave down. So 8 is, the x value of 8 is where a possible point of inflection was. We just showed that since the concavity did not change at 8, that this is not a point of inflection. So that tells us there are no points of inflection here. I promise we're getting close to the end. The next step we need to do is go back and figure out whether the critical value of x equals 6 is a relative max or a relative min. And I think I want to use the first derivative test to check this out. So the first derivative test states we can put the critical value here and make a sign chart. And we pick a test value over here. I'm just going to pick 5. And we substitute it back into the original function. The first derivative. And we pick a number over here as long as it's less than 9, because our graph does not exist past 9 by way of domain. And we are going to substitute that into the first derivative again. And when you do this, you'll see that f prime of 5 gives you back a positive value, which means the graph is increasing there. And f prime of 7 gives you a negative value, which means that the graph is decreasing there. And since the graph goes from increasing to decreasing, this is a relative max at x equals 6. And even better than that, we know the original function is this, and we can substitute the 6 right in here to find the y value of our relative max. And when you do that, you'll see that the relative max actually happens at an ordered pair of 6, 6 square root of 3. On to the graph. So from all of the previous pages, here is all of the relevant information. And in addition to that, we know that f prime of x is bigger than 0 from negative infinity to 6, and f prime of x is less than 0 from 6 to 9. So I'm going to draw a graph over here on the right. And I know the graph does not exist to the right of 9 by the domain. I know I have an x-intercept here at 9, 0. I'm going to do all of the intercepts in red. So there's an x-intercept. There's an x-intercept at 0, 0, which also happens to be a y-intercept. So I'm going to label these 0, 0. I can tell you that the graph increases all the way until 6. So right about here. And in fact, that's where the relative maximum happens. So over here, if you simplify this down into a decimal, you get something that is just greater than 10. So I'm going to come up here to 10 and put the point right here. It's just a little bit above 10, so 6, 6 square root of 3. There are no points of inflection, no minimums, no asymptotes. So I know that to the right of this point here, that it is increasing. So I'm going to draw the graph in blue. I know it's got to go through the x-intercept, and it increases until this point right here. And then after that, it'll go down and it'll decrease all the way until the x-intercept, and that's it. That's our graph. Our graph stops at 9, 0. So here's the sketch of the function f of x equals x square root of 9 minus x.